So a lot of people like sort of non-Humean accounts of laws and chance. So these are accounts where the laws and chances don't supervene on the distribution of local qualities. So for example, on a non-Humean account, we take some simple coin flip world like this. All that happens there are these 10 coin flips. Then on a non-Humean account, it could be, for example, that the chance of heads is 50%, and heads comes up about as frequently as you'd expect. It could also be the case that the chance of heads is 10%, and the heads happens statistically more frequently than one would expect. On a Humean account, by contrast, these factors are just going to fix what the chances are. You couldn't have different kinds of chance distributions that would be assigned to the same Humean mosaic. Okay, so like some of the people in the audience, and not other people in the audience, I'm sort of attracted to non-Humean accounts of laws and chance. But there are certain sort of persistent worries I've had with the sort of the extant accounts, non-Humean accounts that I've seen. So here's two worries regarding chance that every non-Humean account I've seen has at least one of. So the first worry is that most non-Humean accounts have difficulties accommodating statistical mechanical chances. So statistical mechanical chances are compatible with deterministic laws, and they're relative to macrostates. And most Humean accounts have a hard time making sense of chances like that. Humean accounts, by contrast, have an easy time. So Barry's convincingly shown this, I think, and other people have picked this up. But non-humans, at least statistically, have had a much harder time making sense of these sorts of chances. Now, as a side note, of course, one could avoid these worries if you thought that statistical mechanical probabilities should be understood as measures of indifference or something like that. But there's sort of well-known objections to these approaches, like objections David raised, that I think are pretty convincing. So I take that not to be an option. Here's a second worry, maybe even more pressing worry, is most non-Humean accounts don't have enough structure to answer, or at least offer plausible answers to questions that I think any adequate account should answer. So for example, if there's a chance of A, some proposition at one time, is there also a chance of A at another? Let's take Armstrong's account. You got some necessitation universal, and you got a F and a G, and you got a 0.4 at the bottom for some reason. So at another time, is there also be a chance of A? And if so, how are these chances related? Armstrong's account just doesn't tell you anything about that. No idea what we should say about that question. Or for another example, what justifies the assignment of the particular numbers of chance events that we assign? So one possibility is, I guess, there are brute relations of numbers. I guess Armstrong could say, oh, the reason that I was justified in writing that 0.4 subscript when I wrote that NFG is because n also bears this relation to the number 0.4. But that sounds, hopefully to us, all sort of crazy, right? And there's no particular reason that 0.4 should be the number, and we could do chances on a scale of 0 to 2, and it would work just as well. A more plausible story would be, okay, now these numbers represent some deeper underlying structure that justifies these numerical assignments. Okay, great. So, and what is that structure exactly? And again, for example, Armstrong's account isn't going to tell us anything about that. So here's the project. I want to sort of sketch a way of providing a non-Humean account of laws and chance that avoids these two worries. So that is, it provides an account of statistical mechanical chances, can accommodate them, and it yields the structure you need to answer the kinds of questions of detail that I described, like those I described on the last slide. And here's just the one-page preview summary of how I'm going to proceed. So I'm going to adopt a broadly Lewisian picture of metaphysics, and I'm going to posit a single fundamental relation that satisfies certain constraints. Then I'm going to show that doing so will yield certain things which look a lot like laws and chances. And then my claim will be, those things are the laws and chances. So that's how it's going to go. Okay. So brief aside, you might wonder, why adopt a Lewisian account of metaphysics? I thought Tim might be here, so this slide was half aimed at him. This is the question Tim would ask. Why adopt a Lewisian account of metaphysics? Okay. So a couple reasons. main reason is because it's perhaps the most comprehensive and detailed metaphysical framework on offer. So I think that, for one, makes it sort of intrinsically interesting to see how you could work out an account like this in such a background. More importantly, is it really forces you to answer various questions of detail. I mean, it's easy when doing this sort of thing to just forget about certain kinds of objections or problems or issues if you just consider this project in isolation. But if you try to plug it into a deep, comprehensive metaphysical framework, various questions come into focus which don't even occur to you. This certainly happened to me working. A whole bunch of questions came into focus. It wouldn't even occur to me if I didn't try to plug it in to a completely specified, worked out account. And likewise, because of that, I think if this approach is successful, then it offers sort of a proof of concept that this sort of approach can work. So even if you don't like all of Lewis's metaphysical commitments, it offers you sort of a roadmap or a blueprint for maybe how to approach these questions in a way which, at least I think, will be more satisfactory, and do something like that given different kinds of metaphysical assumptions. Why do I say only broadly Lewisian? And the main reason, of course, is that Lewis himself was a Humean about laws and chance, and I'm not going to assume that. Also, as we'll see, I'm going to suggest at least one minor revision to some of the things Lewis says. That sort of comes out as plausible, I think, given this kind of account. So I'm not wedded to this stuff. Wedded to everything Lewis says, in any case. So here's how the rest of this talk will go. First, I'll go briefly sketch some of Lewis's framework that I'll employ for the rest of this talk. Then I'll sort of sketch the nomic likelihood account, which is my name of the week for this proposal. I'm not really sure what to call it. If you have a better idea for a name, then let me know. And I can do this in sort of 3 stages. First, I'm going to sort of describe the main metaphysical posit in a bit more detail. Then I'll describe the sort of what the proposed analysis is going to be. And then I'll talk a bit more about the axioms and some of the issues, the representation theorem, and uniqueness theorems that come up that I think are interesting. Okay, and then I'll end by talking about 2 sorts of kinds of interesting consequences, I think, of this project. So one consequence regarding what kinds of chances are intelligible, and another consequence regarding how to think about certain features of Lewis's framework. Okay, so a quick crash course background in Lewis's framework. I suspect a lot of you here have taken classes with Barry, so you guys can just zone out. Take out your phone. You know all this. So here's sort of one way of building up Lewis's framework. So we start by assuming the existence of some set of possible individuals. I say set or class. I'm going to run roughshod over that distinction, like the mathematical Neanderthal that I am. Okay, so the existence of some set or class or whatever of possible individuals. We identify properties with sets of these guys, or for n-place properties, or identify them with sets of ordered n tuples of possible individuals. And here's our second sort of posit. Then we identify some of these as the perfectly natural properties. These will, in the end, if we set things up correctly, end up providing a minimal supervenience space for all of the contingent truths. Okay, and then once we have this stuff defined, we can start characterizing various things. For example, characterize the notion of duplication, or as I'll call it, L-duplication, for reasons that will become clear later. We say 2 things are L duplicates, if and only if you can form a bijection between them and their parts that preserves all of their perfect natural properties. We can also characterize things like what it is to be an intrinsic property. We can say that intrinsic properties are properties that never divide, or L intrinsic properties are properties that never divide L duplicates. Okay. Here's the third posit. Some of these perfectly natural relations we're going to designate as the world-building relations. So the ones we use to sort of, as it were, delineate when 2 things belong to the same possible world. And once we've made this third posit, then we can build possible worlds. So we look at all the possible individuals. We look at sort of chains of them closed under world-building relations, and then take those fusions of possible individuals, and those are going to give us the different possible worlds. So an aside question. So you might wonder, why not just make all of the perfectly natural relations world building? I think everyone who's read Lewis has this thought. Why not just say that they're all world building? I think that is a natural thought, but I also think Lewis had a good reason for being hesitant about that. So this is something he talks about on plurality, is basically his worry is about people who want to adopt, say, sort of measurement theoretic approaches to properties like mass or charge. So people like that are going to posit perfectly natural relations like, say, same charge as, or well, that's Lewis's example. Maybe more charge as is actually the kind of thing they would use. And if we take that to be world building, then I guess any links of possible individuals with anything with charge, intuitively, any possible world will all be in fact one big world. We do the same thing with mass, whatever. Basically, end up with just one possible world, one like, very strange, bizarrely linked possible world, and that's not what we want. So we want to rule out things like that. We want a distinction between the world-building relations and the non-world-building relations. Okay. Finally, now that we have possible worlds, we can characterize propositions. So propositions are just sets of worlds. Note, given what we said, it will also follow that every proposition is also a property. So a world is a possible individual. Propositions are sets of worlds, so propositions are sets of possible individuals. So every proposition is identical to the property of being a world, basically, where that proposition is true. Good. Okay. That's the Lewis background. So here's the proposal in 3 stages. So here's the first stage. So I'm going to use this notation, C sub AW, as just a way to describe an ordered triple consisting of a pair of propositions in a world. So the C and the A are supposed to be sort of mnemonically helpful. C is sort of like consequent, A is for antecedent or background or something. That's how you can think of it. But really it's just, right now it's just a triple of a pair of propositions in the world. So here's the first part of the count. This is the metaphysical posit. Claim is there's a unique, perfectly natural 6-place relation, which I'll use this sort of notation for, slightly curvy greater than or equal to sign. And intuitively, you can think of this relation as C given A at W is at least as nomically likely as C prime given A prime at W prime. So there's a unique, perfectly natural 6-place relation such that, first, whenever it holds, all those propositions it holds of supervene on all the perfectly natural properties, not including this nomic likelihood relation. That's basically saying this holds of propositions which aren't themselves about the laws and chances. Certain kinds of regress and circularity worries you get into if you don't say that. And second claim, importantly, I'm going to say that this relation satisfies all of the nomic likelihood axioms. I haven't said what those are, but we'll get to that. But that's the posit. The posit is that there's this unique, perfectly natural 6-place relation that satisfies these properties. Okay, brief interlude to introduce a bit of terminology. So I'm going to use L's to stand for proposition that picks out a set of worlds and a certain way of partitioning worlds, where all of the worlds in each cell of the partition basically share all the same nomic likelihood relations. This will end up being the partitioning worlds into worlds with the exact same laws, but we can't assume that yet, right? That's supposed to fall out of the account. That's why I'm using L there, for example. I'm going to do CH, so CH sub L A of C. So this is going to be a function which takes 3 propositions as arguments and spits out a real number. Let NR and NF be relations that hold of these triples. And I'll use omega to stand for the set of all possible worlds, an empty set to stand for the empty set. And then I'll use these things. So this is sort of the curvy greater than and the tilde to stand for the nomically greater than and nomically on a par with relations. And those are just defined in terms of our primitive in the usual way. Okay, good. So you can prove the following. I've proved the following representation of uniqueness theorem. If this nomic likelihood relation satisfies all the nomic likelihood axioms, then there's a unique function CH and unique pair of relations NR and NF such that these 4 conditions are satisfied. The first, the actual clause is slightly more complicated than this, but I'm going to gloss over that. Basically, the chance of a proposition is greater or equal to the chance of some other proposition if and only if the nomic likelihood of the triple corresponding to the first chance is greater or equal to the nomic likelihood corresponding to the second one. CH sub L of A satisfies the countable probability axioms. So it's a countable probability function. NR holds a triple if and only if that triple is nomically on a par with the tautology. So NR is the nomic requirement, intuitively. And NF holds a triple if and only if that triple is nomically on a par with the anti-tautology, or the empty set. That's nomically forbidden, so that NF is intuitively standing for. And so here's the proposed analysis. Identify the complete laws of nature with the propositions L, or equivalently, if you like, with a property of being some world in L. And identify the possible laws of nature, not just the complete laws, with any sort of disjunction of L's that you like. Identify the chances with this CH function, this representation uniqueness theorem gives you. So that is the chance of C given complete laws L and background A is X, if and only if we take this CH function the representation uniqueness theorem gave us, CH sub L of A of C is equal to X. And we identify nomic requirements and nomic forbiddings, likewise, with the NR and NF relations picked out by the representation theorem. So if A holds, then C is nomically required at W, if and only if NR holds of that triple, and likewise for nomic forbidding. So that's the proposed analysis. Okay, so third part. So let me take a sort of brief interlude here. So any of you who've worked in measurement theory or Savage-style decision theory or whatever are probably thinking at this point that, picking out the relevant axioms and then working out the representation theorem should be a total piece of cake. Because look, in the literature, there's just a bazillion representation theorems, which take orderings over some batch of things. Maybe it's, preferences. Maybe it's, standard measurement theory of objects of a certain kind or whatever. And you take an ordering of these guys that satisfies certain constraints, and then you show there's unique probabilistic representation. There's just bazillions of results like that. So just take one of those, change how we're understanding the ordering things and what the elements are, slap it in, and we're done. So that's what I thought, too, when I started on this project. And if it had been as difficult as I thought, I would never have bothered doing it. So there's several complications that arise. So I'm just going to flag sort of two of the especially troublesome ones, as it turns out. So here's sort of one complication, is I think you really want the chance of A being 1 and the chance of A being 0 to be distinct from A being nomically required and A being nomically forbidden. There are, after all, lots of things like, say, the chance of countably infinitely many coin tosses, all landing heads. The chance of that is 0, but it's not nomically forbidden. It can definitely happen. And likewise, there are things which have a chance of 1 which aren't nomically required. So what you need to end up doing is, in addition to having the standard largest and smallest likelihoods, you need to posit a unique next smallest and next largest likelihood. I end up calling it a mega minus and empty set plus. And this causes a lot of headaches. So for example, one of the key axioms in pretty much any of these representation theorems is a kind of qualitative additivity axiom. So that just turns out to be false once you add these guys in. And since pretty much every lemma you use in standard approaches just uses the qualitative additivity axiom over and over again, you got to redo all of that. So that's one kind of headache that arises. Here's a second sort of complication, is every representation theorem that I know of this kind requires some really strong richness assumptions about the orderings that amount to, among other things, basically every chance value being instantiated in some way. The exact details vary a little bit depending on the representation theorem in question, but also this generally assumes that, for example, for any chance event, we can arbitrarily subdivide it into smaller events of arbitrarily small probabilities. We can do that in any way you like. And I don't think we should assume that. I think we definitely shouldn't assume that. I think the following is totally possible. There's a world in which there's exactly one chance event. Either A or not A. A is a chance of 0.6, not A is a chance of 0.4, and that's it. Right. There's a chance of 1 that either is going to happen, a chance of 0 that neither will happen. Right. We should be able to make sense of a world like that. And that world should be distinct from a world in which there's only one chance event, and the chances are 0.7 and 0.3. So the tack I end up taking is I end up sort of positing cross-world relations of various kinds that allow you to effectively sort of import richness from other worlds, sort of steal them in. But then that also requires revamping various kinds of things. So here are what the 11 nomic likelihood axioms are. So on the handout, I give a sort of gloss of each of these. And in the appendix, I give the sort of the detailed formulations of these axioms and also some of the important lemmas that follow from them. So I was originally going to sort of just talk through the glossary of these axioms, but I was talking to my wife about this, and she's like, no. No. So I do what my wife says, so I'm not going to do that for all of them. I'm just going to say some general things about them. Then I will talk about some of them a bit more detail, because I think it's worth doing so. They're interesting. So here's a couple interesting things to note. First is, strictly speaking, you only need the first 7 axioms to prove the representation and uniqueness theorem. So these last 4, in fact, just further substantive constraints that you don't actually need to get the representation and uniqueness theorem to work out. Second thing as far as what these axioms are like, so 3 of these axioms are just completely bog standard axioms, which you'd find in pretty much any representation theorem that's going to give you a countably additive probability measure. There are 3 more of these which are not at all standard, but I think are uncontroversial, which is to say, I sort of thought about it for about 15, 20 seconds, and I couldn't think of somebody who would be really unhappy with this, at least assuming that we're looking for real value probabilities. So I think those are relatively uncontroversial. And then there are these 5 which are maybe possibly controversial. So I'm just talk through briefly each of these 5 axioms because I want anybody who wants to climb on board to sort of know what they're getting into if they do that. So here's the first of these. So it's the rich world axiom. So this basically posits the existence of some rich world where every nomic likelihood ends up being instantiated. So for every triple that obtains at any world, there's some triple at this world which is nomically on a par with it. And it also tells us that at this rich world, there's a unique next most likely, a next most likely and next least likely events, the omega minus and the empty set plus events. So, I think these are plausible things, but of course these are things that one could reject. For example, this makes a particular kind of modal claim. Somebody might have a modal picture in which they just want to reject the thought that there's some world where every sort of degree of nomic likelihood is instantiated. Here's another axiom, so axiom 8. So it'll follow from the way things are set up that you can have triples that play a role in these nomic likelihood relations even if the C and A in question are all both false at W. This basically amounts to the fact that this framework basically allows there to be uninstantiated laws at a world. What axiom 8 says is that, yeah, effectively, you can have uninstantiated laws, but you can't have necessarily uninstantiated laws. And again, I think that's plausible, but that's something somebody might resist. And you might think, no, maybe there can be certain kinds of cases where you have laws that are just necessarily uninstantiated. Here's a 9th axiom, so chance instantiation. So this is one of the most intuitive of them. This basically just says if you have some middling nomic likelihood assigned to a triple, then there's going to be some world with the same laws, where A is true, where that event happens, and some world where it doesn't. So if there's a middling likelihood assigned to a coin flip, there's going to be some world with the same laws where it lands heads, and some world with the same laws where it lands tails. That's a pretty natural thing to say if you want states to look like chances. Again, not completely controversial, so typical Humean pictures of chance are going to want to reject this axiom. So take a simple coin flip world, say that's the actual world. They might plausibly assign a chance of heads or tails being 1/2, and maybe taking these probabilities to be independent. And so they'll assign a positive chance to a world in which all the coin tosses land tails. But it's not the case that there's some world with the exact same laws where this happens. So in a world like this, of course, the laws would be all coin tosses land tails, or something like that. And here are the last two. So the 10th axiom is sort of same algebra. So basically, if you sort of fix on a world, then you can plug in different sort of antecedent propositions to get different chance distributions. And axiom 10 says, once we've fixed a world, the algebra of propositions to which chances are assigned is going to be the same. Now, again, I think this is plausible, but this is not going to be completely uncontroversial. So, so the most salient view, or person who might want to resist this, is something maybe like Callender and Cohen, and maybe Karl Hoffer in some of his work, who want there to be different layers of chances assigned to different things. And you might plausibly think that the algebra propositions to which chances are assigned at these different layers are, of course, not going to be identical. So somebody like that would want to reject this axiom. Similarly, the 11th axiom tells us roughly that if we fix in a world and we look at the chances assigned to propositions, when we vary the antecedent proposition, then those end up being related effectively in the way that you would think that conditionalization should say they are. Again, I think this is pretty plausible, but again, for example, the Callender and Cohen or Karl Hoffer view, I think, might want to resist this if they think that the chances assigned to these different things should be able to be independent in a certain kind of way. Because then you can have possibilities like, say, there being statistical mechanical chances assigned to a whole bunch of things. We have maybe behavioral science chances assigned to some subset of the algebra. And then those can end up not lining up in such a way it's just that you can basically derive the probabilities of the behavioral sciences from those statistical mechanics by conditionalization. So that would be another kind of view which we want to reject this 11th axiom. OK. So there. That's the proposal. Oh, yes?
Is it just a word about continuity?
Oh.
You skipped over that too, continuity. I just wanted, if there's just a sentence for that.
Oh, so it's the continuity axiom. So it's one of the standard axioms which people appeal to when showing that the probability function is going to be countably additive. No, sorry, that was not helpful. I do not have a good simple gloss that off the top of my head. But that's functionally why it's there. And that's one of the three bog standard ones, which you would just see pretty much any representation theorem, you sort of see something like that. So maybe you're looking at it and you're like, no. So it's one of the things you need to plug in to end up getting countable additivity. Okay. We'll talk about some consequences of this particular approach. So first, what sorts of chances are going to be intelligible on this approach? So on the nomic likelihood account, so chances are compatible with deterministic laws. For example, it's sort of straightforward to see that you can have, for example, some antecedent proposition describing maybe a complete state of the world at a time, and some other proposition C about, say, some future or past event, and it being the case that basically the NR relation, the nomic requirement relation, holds for some of those, and nomic forbidding relation holds for other those. And that's completely compatible with there being, say, chancy nomic likelihoods holding between different, say maybe less specific, weaker antecedent propositions. So it's relatively straightforward to end up having, say, deterministic Newtonian laws and non-trivial statistical mechanical chances regarding things. Maybe like the various likelihoods of initial conditions or something like that. Likewise, on this account, chances can be macrostate relative. There's no problem making sense of that. You just vary what the antecedent proposition is to match the macrostate we're thinking of. That's also straightforward. So as one would expect, given that this is constructed in part to yield statistical mechanical chances, the nomenological likelihood account can accommodate statistical mechanical chances. Is that a question? Or? No. Stretch away. Stretch away. All right. Here's a more interesting case. So actually, Ned also brought up a case similar to this. It's a simple time travel scenario. This is from a Stanford Encyclopedia entry by Frank Artzenius and Tim Maudlin on time travel in modern physics. So say we have this very simple world. So it has one spatial dimension, of course, one temporal dimension, and the space-time topology is such that anything which hits this inside part of this edge will come out the corresponding place on the lower edge and continue on. So if we send a particle sort of going at this velocity, at this time, this direction, here's what it's sort of going to look like. If we're just sort of focusing on what things will look like positionally, it'll be one particle, one particle, one particle. Then at this time, whoop, two particles appear. Two particles, two particles, two particles. Then whoop, one of them vanishes, and it keeps going. But what actually happens is you had one particle which came here, traveled back in time there, and kept on going. Okay. So what's going to happen when we send a particle, say, on this trajectory? So here's one thing that could happen. But here's another thing that could happen. So the particle would go in. First I'll describe sort of what's actually happening. The particle will sort of go in. It'll travel back in time. It'll keep on going. Then it'll, bam, it'll hit this other particle. And it'll come to a halt. This other particle will be sent off. And it'll sit there, sit there, sit there, sit there, sit there, get hit by its prior self, and then get shut off. Or if we're just focusing on the x-axis, it'll be one particle, one particle, one particle, three particles. These guys go and bam, they hit each other. Three particles, then boop, two of them disappear. Then we have one particle going off. And in fact, if you think about it a bit, you can see that we can drop any number of parallel lines here, and we'll get another consistent solution. Consistent solution with everything we've said. So in fact, as far as what's going to happen, there are infinitely many things that could happen given what we've said so far. It's not determined, as it were, by what we've said about the dynamics. Well, I didn't even describe those to you. It's like Newtonian mechanics with inelastic relations or something. Okay. Here's what Artesians and modelists say about this case. They note that this is interesting. We have an odd sort of indeterminism. The complete physical state on S does not determine the physical state in the future, even though the local dynamics is perfectly deterministic, and even though there is no other past edge to the space-time region in S's future. There's nowhere else for boundary values to come from, which could influence the state in the region. The dynamics does not even supply any probabilities to the various possibilities. So it's not even like quantum mechanical indeterminism. But you might ask, is it possible for there to be chances of this? Is it possible for there to be a chance of, it not, maybe a 10% chance that it's not going to hit anything, 10% chance it's going to hit itself twice, 40% chance it's going to hit itself 77 times, and I forgot how many percentages I had, but I don't know. And the rest is, hits itself 1,000,000 times, whatever. Is it possible to make sense of chances like that? So on the nomological likelihood account, yes, for now you can make sense of chances like that. That's not pro or con. That's just interesting. Hey, guess that makes sense. This ends up being intelligible on this account. So here's another interesting consequence of this approach. So here's an objection you might have, I think a natural objection you might have to this proposal. So on this nomological likelihood account, sort of L-duplicate worlds needn't have the same laws. So one way to see that is basically all the nomic stuff ends up supervening, ends up being sort of generated from this nomic likelihood relation. And that's the relation between pairs of worlds and four propositions. But because that's what the structure is, you could have a world which is a duplicate of, say, you have two worlds which are duplicates. That is, with respect to themselves, they bear the same perfectly natural properties, and they're parts of the same perfectly natural properties, and they all bear the same perfectly natural relations to each other. So they could be L duplicates, and yet one of them could appear in one of these nomic likelihood relations and the other one not. So different nomic likelihood facts would obtain, and so they can have different laws. And so you can have L duplicate worlds just don't have the same laws. And that seems kind of weird, right? Like, oh, the world is just like this other one. Are the laws the same? Well, no, the laws aren't the same, but it's exactly like this other one. In a similar vein, it's going to turn out that the complete laws of a world are extrinsic, L-extrinsic properties of the world. And that sounds kind of funny. The laws of the world are extrinsic properties of the world. So here's the reply I'm going to suggest. So I think actually I'm going to suggest that we should reject Lewis's analyses of duplication and intrinsicality. And I think actually we have sort of independent reasons to do this. So let's take a step back for a second. So let's consider a sort of paradigmatic instance of a perfectly natural non-world building relation. So on sort of standard measurement theoretic accounts of mass, this might be a sort of more mass than and mass concatenation relations. So, right, that's what I said, right? So it's standard measurement theory approach. You use these relations to characterize, say, all the mass properties, characterize what the 3 grams of mass property is and the 5 grams of mass property is, and so on. But note that the up and the charm quarks differ only with respect to their mass. They're like respect to all their other perfectly natural properties. So it's going to follow, if we buy this measurement theoretic account of mass, that the up and charm quarks are in fact L duplicates. And it's also going to follow that having, say, 2.2 mega electron volts over c squared mass property will actually end up being an extrinsic property of a particle. Both sort of uncomfortable consequences. And of course, it gets worse. Say we do adopt a similar measurement theoretic treatment of charge and spin and all that. In fact, hey, all of the elementary particles will be duplicates. And all these physicists complaining like, oh, 64 particles, it's too inelegant, right? No, they're all duplicates, man. It's so simple. This is just one thing. Here's a different approach one might take here. Let's say that 2 objects are interchangeable with respect to a relation. If the relation holds with respect to one of the objects, if and only if it also holds with respect to the other, whether plugged into the same appropriate slots. Here's an alternative characterization of duplication. I'll call it O duplication. So the O is for ordinary duplication, but that's strictly speaking question begging, so I'm just using a letter there. Okay, O duplication. So 2 things, O1 and O2, are O duplicates if and only if 1, basically they're L duplicates. So we can construct a bijection between them and their parts that preserves perfect natural properties. And 2, these objects are interchangeable with respect to all the non-world building perfectly natural relations. So if we adopt this account of duplication, then the up and charm quarks won't be duplicates, given the standard measurement theoretic account of mass. There will be L duplicates, but they're not interchangeable with respect to all the non-world building relations. In particular, say, the more mass than or mass concatenation relations. They won't be interchangeable with respect to those. So they won't end up being O duplicates. Likewise, we can characterize the O intrinsic properties as the properties that never divide O duplicates. And it'll turn out that, say, having such and such amount of mass will turn out to be an O intrinsic property of a particle. Okay, so let's go back to this nomic likelihood relation. So I've said it's a perfectly natural relation. Is it a world-building one or a non-worlding one? Well, you think about it for a bit, it better be a non-world-building one, right? It's a relation between pairs of worlds and, I guess, sets of worlds. And if this relation holding between, for example, pairs of worlds is enough to make them the same world, then you're going to get one big, ugly world. Maybe there's some world intuitively where there aren't any nomic relations. Maybe those got to be separate things. But basically, you get one big world. So this better be a non-world building relation. But if that's true, then on my account, O duplicate worlds will in fact, it'll in fact be the case that O duplicate worlds must have the same laws. They won't be L duplicates, but they won't be interchangeable with respect to a non-world building relation. So in fact, they will be O duplicates. Likewise, on NLA, the complete laws of nature will be O intrinsic properties of the world, just like we'd like. So my suggestion is that maybe the moral we'll take from all this is that our ordinary notion of duplication corresponds to O duplication, not L duplication. And likewise, our ordinary notion of intrinsic properties really corresponds to O intrinsic, not L intrinsic. And if we do that, then if we make this little tweak to Lewis's account, then we don't end up, in the end, with those unpalatable consequences of the nomic likelihood account. Okay, that's it.